So we finished off with the previous problem, which was a stoichiometry problem, and I saved this one for today so that we could kind of review that before we go on to the next topic, which is just an extension of stoichiometry. So this is another stoichiometry problem. The component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and water according to this simplified equation. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate O2 and H2O, what mass of HNO3 in kilograms can form from this amount of NO2 pollutant? Okay, so read through all the words. A lot of those words are backstory, background information. The important thing in here is 16 grams of NO2, what mass of HNO3 in kilograms. Stoichiometry problems end up being unit conversion problems, and so we need to know what are we starting with and what are we going towards. So 16 grams of NO2, 16 kilograms of NO2, so 16 kilograms of NO2. And what mass of HNO3 in kilograms. So what's the path for stoichiometry? Grams to moles to moles to grams. Now, what's a little different about this one? Kilograms. I just thought of a new way to deal with the kilo in this problem. Ignore it. Pretend it isn't there. So I'm going to do that method because I've never done it on a video before. There's two other methods. One method, you would take your kilograms and convert to grams at the beginning, and you take your grams and convert back to kilograms at the end. That's very straightforward and less confusing, so some students prefer to do that. The other way I've done it is we just set aside the kilo. It's in the problem, but we just set it aside and bring it back. Because what happens is that this kilogram to gram conversion and the gram to kilogram conversion end up canceling each other out, right? But I'm going to try something different. We're going to pretend the kilo isn't there. So we're going to answer a slightly different question, and then we'll deal with that. So we're going to start with 16 grams of NO2 and find out how many grams of HNO3. Okay? So 16 grams of NO2, and I'm going to convert that to moles of NO2, grams to moles, and then I'm going to go to moles of what? HNO3, the thing I'm trying to find. And from moles of HNO3, I'm going to go to grams of HNO3. The previous unit comes down here in the denominator because I want those to cancel out. All the units are in place. The numbers we need are molar masses that we calculate using the periodic table and the chemical formulas, and mole ratios from the balanced chemical equation. So in the chemical equation, we see that 4 moles of NO2 produce 4 moles of HNO3. So 4 moles of HNO3 come from 4 moles of NO2. And 4 over 4 is 1. Yeah, you could cancel that out, but you can also just leave it there. Then we need the molar mass of NO2 and the molar mass of HNO3, and so we need to calculate those. So for HNO3, there's an H and an N, and 3 oxygens. So 63.018 grams is equal to 1 mole of HNO3. So over here, where I need the mass of a mole of HNO3, I'm going to put this mass in that I just calculated. And then I also need the molar mass of NO2, 1 nitrogen, and 2 oxygens, 46.01. Molar mass of NO2. So 1 mole of NO2 is 46.01 grams. Do you have any questions? No? Okay. So now I'm just going to run this through my calculator. 16 times 1 divided by 46.01 times 4 divided by 4 times 63.018 divided by 1. And I get an answer that is 21.91. And there's a whole bunch of digits. And so as I'm starting to write those down, I'm going to say, well, how many significant figures do I actually need? 2. This starting number only had 2, so that means I need 2 significant figures in my answer, so I've already got enough, right? And that would be, well, let's see. I didn't leave enough space here. I wrote too wide. 21.91 grams of HNO3. Anybody else get that number? My calculator tell me the truth? Well, nobody's disputing it, so we'll go with that. So now, what about the kilogram? So if I started with 16 grams, how do I get to 16 kilograms? Well, I really can't convert. I mean, 16 grams is a different amount than 16 kilograms, right? This is 1,000 times bigger than that. But if 16 grams gave me 21, well, it would round to 22, gave me 22 grams, then 16 kilograms would give me 22 kilograms. Oh. It'd be the same. So let's see. If we had, I need a good analogy. What's something you buy at the store?
Pickles and eggs.
We'll go with eggs. I don't like pickles. So you're getting a dozen eggs and it's $2. If you get 10 dozen eggs, how much is it? It's 10 dozen eggs would be $20, right? If I'm getting 1 dozen or 100 dozen, it's $2 or $200, right? Because I'm multiplying both things by the same amount. right? Or I hate to keep using dozen, but it's just such a useful thing. So if I have, let's see, 2 bicycles, how many wheels are there? 4 wheels. If I have 2 dozen bikes, how many wheels are there? In dozens. 4 dozen wheels. Does that make sense? The number is the same. I'm using a bigger unit, but I'm doing the same thing to both sides. Does that make sense? And you can prove this to yourself by doing it the long way up here. And what you'll see is that the kilogram to gram conversion and the gram to kilogram conversion cancel each other out. And if you find it confusing to take a shortcut like this, then don't do it. You can do it the long way. The long way always works. But this can save you a lot of time. So our answer is 22 kilograms.
So the shortcut only works
When the initial unit and the final unit are the same. So this was giving us 16 kilograms and asking for kilograms. If I had 16 kilograms and it was asking me for grams, the units are different. I can't do that. So I've never done it this way before, and I'm not sure if it's necessarily a good way, but there it is.
Would it work if we did like 16 kilograms and then for 46.01 convert that to kilograms? Or would that give us a different answer?
No, you could do that.
I mean, it's like, sure, I'm just trying to understand the flow
Right.
of it.
So 16 kilograms. So we know this is true. 1 mole is 46 grams. Well, what if we had a kilomole? That's 1,000 moles. That would weigh 46 kilograms. All these conversion factors, the numerator is equal to the denominator. It's a fraction. If I multiply the top and the bottom by the same thing, it's still the same value. They are all equal to 1. If I had 4 kilomoles of HNO3, that would be 4 kilomoles of NO2, 63 kilograms and 63 kilomoles, and then over here I'm going to get kilograms. Now that makes sense to some people, it doesn't make sense to other people. On the one hand, it's great that there's lots of different ways to think about it, and on the other hand, it's really confusing because different ways work for different people. What I'd like you to be able to do is think of these metric prefixes as numbers that you can factor in and out. They're powers of 10. And so I can factor the kilo out, or I can factor it in. So if I need kilograms, I can just make it kilomoles because I know the gram to mole. You can put kilo in front of anything. Any questions? Yeah.
Instead of having 4 HNO3, if that was a different number, let's say it was a 3,
Mm-hmm.
then how would it affect the middle portion of that equation, 16 times?
Well, if like this one was a 3,
Yeah, let's say that was a
if this was a 3, I can make it a 3.
Yeah.
So I will do that. Let's, this is getting very colorful. If we make that a 3, then in front of HNO3, which is this one, this 4 would have to be a 3.
Okay. That's the only thing that...
That's the only thing that changes. So the molar masses are always calculated the same way. You use the chemical formula, you're calculating the mass of 1 mole. So this part is going to be the same. The molar mass of HNO3 is always the same thing. And over here, NO2. The coefficients from the balanced chemical equation only show up in the mole ratio. Sometimes people want to put them in here as well, and that's a world of trouble. It makes things much harder. Any other questions? I'm going to put this back. So 22 kilograms is the answer.